In the previous video, we looked at unit testing. So we saw that in unit testing, we test individual functions or units of a program. And now in this video, we are going to look at different ways in which we can do this. And two ways in which we can do that is through black box testing and white box testing. So we saw earlier that in black box testing, the program is like a black box, right? We are not looking what is inside the program. Whereas in white box testing, we are actually analyzing the structure of the program. So let's look at what black box testing is, right? And as we said earlier, the program is viewed as a black box. It is also known as functional testing. And the key idea is to see how we can design test cases for black box testing, right? Now we don't have access to the structure of the code. So then how do we do it? We do black box testing by examining the input and the output value pairs. And we have no knowledge of the design or code that is required. So what are ways in which we can do black box testing? So the first thing which we really need to do is to determine equivalence classes. Now what are equivalence classes? So the domain of the input values of which our program can take, it is partitioned into a set of classes or which are known as equivalence classes. And for each equivalence class, the program behaves similarly, right? So in a particular equivalence class, for every input data in that class, the program behaves similarly, right? So let's take the example of the minimum value function, right? So we have two parameters, x and y, and we have to calculate the minimum. Now in black box, we do not know the structure of the program, right? But can you think of what the equivalence classes will be for in this case? So the equivalence classes are one set of inputs are where x is greater than y. The other set of inputs is where x is less than y. And the third equivalence class is where x is equal to y, right? And for every equivalence class, for example, x greater than y, so like values like 20, 10, 50, 40, right? Wherever x is greater than y, we need to just choose one value from this entire set, right? The same thing for x less than y and x equal to y. So now let's reflect on this question for a moment. So let's say we have a function called is prime, which takes num as input. Num is a positive integer and it returns true if num is prime. Otherwise it returns false. So what do you think are the equivalence classes for this function? You can pause this video and think about the answer before proceeding. Right? So what do you think are the equivalence classes for this function? So this function is checking if a number is prime or not, right? So for all prime numbers, it will return true. It should return true. And for all non-prime numbers, it should return false, right? So for all prime numbers, all prime numbers form one equivalence class, because you can choose any one prime number from this set, right, to test if this function works properly. And another equivalence class is the set of non-prime numbers. So you just need to choose one non-prime number to test this function. So now that we have found what the equivalence classes are, another important thing which we need to do is do what is known as a boundary value analysis. So as we write programs, right, many a times our tendency is to miss values which are at the boundaries, right, or the boundary conditions. And many programmers, many a times they get confused between which operator to put. Should it be less than or less than equal to, right? So some examples are like, what should the range of values be in a for loop, right? So in boundary value analysis, we examine the values at the boundaries of the equivalence classes, right? And so in boundary value analysis, we design test cases using the values at the boundaries of different equivalence classes. So for example, the function is prime, which we just saw, right? Maybe some boundary values are 0 and 1, right? So these are some things which we can check as we design test cases using black box testing. So to summarize, in black box testing, first what we need to do is, from the requirements and specifications, we identify the input and the output structures and the values, right? Because we do not have access to the program, or we are not checking the structure of the program. And then we identify equivalence classes, and then we design test cases such that we identify one representative test case from each equivalence class. And then finally we design boundary value test cases. Now that we have seen what black box testing is, let's look at white box testing. So in white box testing, we analyze the structure of the program, right? And how do we analyze the structure? We use some heuristics, right? And one such heuristic is known as coverage, which means that are we able to execute, or are we able to cover all or almost all parts of the program? And that is one thing which we will try to do as we do white box testing. So this is known as coverage based testing, and there are primarily three ways. One is to do branch coverage, second is multiple conditions coverage, and another way is to do path coverage. Let's look at each of these in detail. So what is branch coverage? So as the name suggests, in a program there are several branches which a program can take, right? So if we have a conditional, if we have a while loop or a for loop, so there are different conditions which the program can take, or different paths which it can, or different branches which it can take. So we check that every branch in the program is accessed at least once, right? And this can be done by making each of the branch condition true or false. For example, let's take the minimum function, right? So if I want to calculate the minimum of two numbers, the condition here is if x is less than y, right? So to achieve branch coverage, I need to check when this evaluates to true, that becomes one test case, and when this evaluates to false, that becomes the other test case, right? So test case 1 is when this evaluates to true, which is take a pair where x is less than y, and the other test case is when this evaluates to false, where x is greater than y, greater than or equal to in this case, right? So choose one pair of x and y such that x is greater than or equal to y. So this is one way in which we can achieve branch coverage. So learners, here is a reflection spot for you. So this is the is prime function, right, which takes a number num and it returns true if it is prime, else it returns false. So what do you think are the test cases that will guarantee branch coverage? Please pause the video here and think about these test cases before proceeding. Right? So for branch coverage, as we saw, we have to check that the condition at each branch, it evaluates to true for one test case and evaluates to false for the other test case, right? So in this case, for this to evaluate to true, for this if condition at line number 2, for it to evaluate to true, num should either be 0 or 1. So 0 or 1 is one test case, right? And for this to evaluate to false, right, it's not 0 or 1. And now here in this case, we have to check if num mod n is equal to 0, right? So this should evaluate to true or it should evaluate to false, right? So when it evaluates to true, that means the number is prime. Sorry, if this evaluates to true, that means a number is not prime, right? So for non-prime numbers, this evaluates to true, and for prime numbers, right, it evaluates to false, right? So in this case, we have one test case which for this condition, then 2 for when it's a prime number, 2 and 3, and 4 when it is a non-prime number, right? So these test cases, they guarantee branch coverage. Now the second type of coverage based testing is multiple condition coverage. So in many cases, right, we can have composite conditional expressions, right? And what we do in multiple condition coverage is to check that each component condition, it takes true and false values, right? So we saw in the previous example of is prime, so we had a composite condition like num equal to 0 or num equal to 1, right? So we check for each component condition. So here num equal to 0 is one component, num equal to 1 is the other component. So we check or we design test cases such that each component condition takes true and false values. So in this case, when num is 0, the first part is true. When num is 1, the second part is true. So the test cases 0, 1, they achieve multiple condition coverage. Now another example is when a number is outside two boundary values, right? So in this example, if you see, we want to do something when num is less than 50 or when it is greater than 150, right? So when it is less than 50 and greater than 150, you do something. Otherwise, if it is within 50 and 150, you do something else. Right? So in this case, let's see how branch coverage and multiple condition coverage, how do they differ, right? So if we had this test case 49 and 100, so 49 will ensure that this is true, right? And do something will get executed. So this ensures that the if condition is true, and 100 ensures that the if condition is false. So hence we achieved branch coverage. Whereas for multiple condition coverage, we also need to check when this is true, right? So we have to add another test case 200, which will evaluate to true, which will evaluate this expression to true, and this remains false, right? And in this case, we can see that in some cases, the multiple condition coverage is a stronger testing strategy than branch coverage. Now, the third type of coverage-based testing is known as path coverage. So what happens in path coverage? We say that the test suite, it achieves path coverage if it can access all linearly independent paths of the program at least once. So what does this mean? So we can see which are the linearly independent paths of a program by constructing what is known as a control flow graph of that program. So let's take an example. So this is the same function is prime, right, which takes a number and returns true if it is prime. And if you see, these are the line numbers, and for each line number I have constructed a node, right? And the nodes denote the line, particular line number, and an edge denotes if the control flows from that line number to the second line number. So for example, we start from line number 1, then at line number 2, we can either go to line number 3, right, and exit the program or the function, or we can move to line number 4. And at line number 4, it is a for loop, right? Either at the start itself, the condition is not satisfied, so we jump to line number 7, or we go to line 5, right? And at line 5, either the condition evaluates to true, in which case we exit the program, exit the function by returning false, or we go back to line number 4. Right? So this is the control flow graph for this function. Right? So what are the paths? The paths are 1, 2, 3, right, which is 1, 2, and this, and we come to this line number. Another path is 1, 2, 4, and 7, right, which is 1, 2, then we go to the 4, and we directly, this for the initial condition itself is false, and we jump to line number 7. Another path is 1, 2, 4, 5, and 6, right? So at line number 5, this evaluates to true, and we exit the function. And another path is 1, 2, 4, 5, right? We come till here, and then again we go back to 4, and then and this can happen multiple times, right? We iterate through this loop multiple times, and then we come out at 7. So these are paths which we determined from this control flow graph. So now learners, here's a reflection spot. Can you identify test cases for each of these paths. So from each of these paths, we can decide or construct a test case. Can you think what these test cases are for each path? You can pause this video and write down your responses before proceeding. So now let's look at the test cases for each path, right? So the first path is 1, 2, 3, right? And by looking at the program, if num is 0 or 1, right? This path, the program flows through this path, right? So that is a test case for this path. For 1, 2, 4 and 7, right? For the value 2, right? The for, we do not enter the for loop, right? We directly jump out. So 2 is a test case for that path. And 1, 2, 4, 5 and 6. So when we reach 6, that means a number is not prime, right? And hence a non-prime number can be a test case for this path. And then for a prime number, right, we have the path 1, 2, 4, 5, and it can go multiple times through this loop and finally come out from 7, right? And since it returns true, that means the number is prime. The number should be prime, right? So these are test cases corresponding to each path. So another way to determine how many test cases and how many paths are there in a program or in a function is to identify the cyclomatic complexity. So we looked at cyclomatic complexity in the previous videos. It is nothing but the number of decision and loop statements plus 1, right? So in this case, we have num equal to 0 or num equal to 1 as one condition, the for loop as having the second condition, num mod n is the third condition. So we have 3 conditions. So the cyclomatic complexity is 3 plus 1, which is equal to 4. And hence we have 4 paths, and hence we need to have at least 4 test cases. So to summarize, in this video, we looked at different ways in which we can do black box testing and white box testing. And we can use these techniques for designing test cases for our programs and modules.